Another way to describe something that exists in 3 space is to use cylindrical coordinates. And basically, cylindrical coordinates take the polar plane and add a vertical z-axis to that 2D system to make a 3D system. It's really similar to the 3D XYZ plane, except for we're replacing the rectangular XY plane with a polar r theta plane. So with cylindrical coordinates, our ordered triples will involve r and theta from the polar plane, and then z to tell you vertically how far to go up or how far to go down. Now we already know how to convert from from polar to rectangular, so to change this picture to 3D, we're converting cylindrical polar to rectangular using very similar equations that we used in the 2D case. The only new equation is the z. But notice that there's nothing really there for us to do with z, because in cylindrical polar coordinates, the z-axis is just like the z-axis in the XYZ system. Let's practice taking a cylindrical point and then translating it into a rectangular coordinate ordered triple. Now the first thing to do is make sure that we recognize that we're working with r, theta, and z. These are not x, y, z values because we're told that we have a cylindrical point, which means these have to take on r, theta, and z values respectively. Once we know what r, theta, and z are, we can plug them into these conversion equations to find out what x, y, and z are. So x comes from r times cosine theta. Y comes from r sine theta. And you can type this into your calculator if you'd like, or you can use corresponding angles. However you want to calculate that, that's what you should do. I like to do most things by hand, so that's what I'm going to do. If I were to think about the x and the y in the polar plane, I would have my polar origin and my polar axis. I would think of a radius of 4 and an angle of 2 pi over 3, which would mean my point would be about right here. I can tell that I'm in the second quadrant, which means x should be negative. Cosine is going to spit out negative values, and I can use a corresponding angle. This angle, I'm sorry, I drew the wrong one. This angle down here is the same cosine value as if I were to use this angle in quadrant 1. The only difference is I need to multiply by a negative. So what I'm going to do is turn this into 4 times negative cosine pi over 3. And the reason I'm going to do that is because I've been able to memorize the values of cosine in the first quadrant, but I can't bring myself to memorize the values in quadrant 2, 3, or 4. So I use everything I know from quadrant 1, and then I apply it by adjusting with a negative or a positive, depending on where I'm at. So cosine at pi over 3 is equal to 1/2. So I would have 4 times negative 1/2. This works out to be negative 2. So the x value for this point is at negative 2. The y value is going to follow a similar pattern. I'm going to replace sine with 2 pi over 3 with sine at pi over 3. Now I don't need a negative here because we're above the x-axis, which means y is positive. Sine is the y values, therefore sine at pi over 3 is equal to sine at 2 pi over 3. And I happen to know that sine at pi over 3 takes on the value root 3 over 2. So the y value that we're working with is 2 root 3. Now the only thing that we have left to do is z, but remember z is equal to z in cylindrical coordinates. There's no work there, we're just going to copy it over. So we have our x value at 2. We have our y value at 2 root 3, and then our z value is -2. So these 2 points are described in different coordinate systems, but they're at the same location. Let's try one more. In this next example, we have r is equal to 5, theta is pi over 6, z is 4, and let's go ahead and plot where we are in the r theta plane. We have our polar origin, our polar axis, we have a radius of 5, and an angle of pi over 6. So our point is probably about right here in the r theta plane. So then x is going to be represented by 5 times cosine pi over 6, and y will be 5 sine pi over 6. And then if we happen to remember what cosine at pi over 6 looks like, we can replace that. So we'll have root 3 over 2, but that's being multiplied by 5. So the x value we're looking at is 5 root 3 over 2. The y value will look like 5 times 1/2, or 5/2. And then the z value gets copied over. Z is equal to 4. So this point in rectangular form would look like 5 root 3 over 2, 5/2, 4. Sometimes we start with cylindrical coordinates and we translate to rectangular. Sometimes we start with rectangular and want to translate to cylindrical. So let's try an example of that. We're starting with rectangular coordinates, so we know these are x, y, and z values. We want to translate to cylindrical. Now the equations that we used on the last slide, technically they're related here, but we need to manipulate them so that we can plug in the values that we know, x, y, z, and calculate the values that we don't know, r and theta. So to find r, we're going to use that Pythagorean theorem, which says r squared is equal to x squared plus y squared. So we find that r is equal to plus or minus root 10. Now conventionally we keep the positive radius. So I'm just going to pick that and say that r is root 10. We could use negative root 10, but we would have to adjust the angle appropriately to make that work. My suggestion, keep the positive. All right, then we need to calculate theta. So theta is found using tangent. So we're going to do tangent inverse of y over x, -3 over 1, or tangent inverse 3. And we can use our calculator here if we want. Tan inverse Unfortunately, tangent inverse of -3 doesn't work out to be a nice neat angle, so we're just going to leave it as tangent inverse of -3. And then the last thing that we need to do is find out what z is. Well, there's no conversion here. Z is equal to 5 in both systems. So the point 1, -3, 5, we can represent that with r, root 10, theta, tangent inverse -3, and z, 5. Now, something that can be tricky is that tangent inverse only returns values between 0 and 180, because tangent is able to complete 2 periods around the entire circle. So we have to make sure that we're really using the right theta to describe where we're at. It's possible that we would need to add 180 degrees to the angle that we get from tangent inverse so that we're in the correct spot. So what we'll do is plot our point, the rectangular coordinates. X is equal to 1, y is equal to -3. So we're like, and then z is +5. So we'd be up here somewhere, directly above that x in the xy plane. If we use tangent inverse of -3, which is, if you're in degrees, it's approximately -71 degrees. Maybe we'll say 72. Approximately -72 degrees. Then we would rotate -72 going this way, which would put us in the right location. Now, tangent inverse does have two solutions, so if you take that tangent inverse of -3 and you add 180 to it, you get 108 degrees, which if we rotated positive 108, that would put us on the other side of the tangent solution. So if that sounds confusing to you, I recommend that you do some review on the inverse functions, inverse trig functions specifically. Tangent does have two solutions within the polar plane, within the xy plane, however you want to look at it. You need to make sure you're picking the correct one. For this problem, we don't have to do anything. Tangent inverse is giving us the correct solution right out of the gate, but that's not always the case. All right, so the point in rectangular coordinates, 1, -3, 5, is the same as the point in cylindrical polar coordinates, √10, negative, I'm going to just write tangent inverse -3, because that's the exact form, and then z is 5. Goodness. All right, let's try one more. Given x, y, z, let's find r, theta, and z. So r is going to come from that Pythagorean theorem, and I'm going to jump straight into that square root there. So we have -8 squared plus +8 squared. That looks like 64 plus 64, which look 28. And we can try and simplify that. That comes down to 8√2. So we have our radius. Next, we need to find our theta. 8 over -8. Tangent inverse of -1. Tangent inverse of 1 is at pi/4, but tangent inverse of -1 would suggest that I need to use a negative angle, and that's because tangent is an odd function. So if I think about using an odd angle to describe how to get to this point, then we can help think about what angle plugged into tangent would give us -1. So let's plot this point in rectangular first. We have -8 in the x direction, +8 in the y direction, so we are in the xy plane quadrant 2. And since I know that we are in quadrant 2, I can use that to help pick the angle that I'm looking for. I'm going to use the fact that tangent is an odd function to pull the negative out, to say I'm looking at tangent inverse of 1. I know that tangent inverse of +1 is pi/4, and we have this negative out front, so tangent inverse of -1 is -pi/4. Now, -pi/4 would put us down here in quadrant 4. But notice, if I add a -pi to that, I'll get exactly along the line that I want. So for tangent inverse of -1, we have two solutions. One would be if theta was -pi/4. The other one would be if theta were -5pi/4. Whoops, those are two. However, only one of these works to take us to the same location as the point that we started with. So we would ignore one of the good tangent solutions and only pick the one that's relevant to our point. And then lastly, z is z. So in rectangular, the point was -8, +8, -7. But in cylindrical, it looks like 8√2. -5pi/4, and then -7 for z just gets copied over. Now it helps to visualize why this is called cylindrical coordinate systems. And I've created an applet in the course that will help you see, sorry, I didn't create the applet. I've embedded an applet that somebody else created to help you see exactly how these coordinates are mapped out along surfaces of cylinders. And I've got a little screenshot here that helps us see that we have the radius that's marked along the positive x-axis. Then we have our theta that tells us how much to rotate away from that axis. And then we have our z that tells us how far up or below we need to travel to get to our point. So this point is described by r, theta, and z. And it literally is traveling along a surface of a cylinder. Now, in rectangular coordinate systems, each one of our variables set equal to a constant gave us a plane. For example, if I were to say let x equal 1, that would be a plane on the x-axis that's completely flat, set of all the points where x is equal to 1, y and z are equal to whatever they want to be. And there's nothing special about x. I could have done that for y as well. That would have been a plane perpendicular to the y-axis at y equals 1, set of all points with the coordinate y equal to 1. X and z can be whatever they like. And I could make the same argument for z, right? A plane that's perpendicular to the z-axis, containing all the points with z equals 1, x and y get to be whatever they want. So in rectangular coordinates, any one of the variables set equal to a constant was a plane. Cylindrical coordinates are not the same. For example, if I were to force r to be equal to 3, this is an equation in cylindrical coordinates, and it does not represent a plane. Instead, if we can think about all the points that we could possibly generate with r equal to 3, I could plot a point right here. I could plot a point anywhere along this curve. I could plot anywhere along this vertical z as well. In fact, I can plot any point on the surface of this cylinder because this cylinder is being described using r equals 3. In cylindrical coordinates, setting the variable r equal to 3 creates a cylinder with radius 3. So the same way that x equals 1 is a plane in rectangular coordinates, r equals 3 is a cylinder in cylindrical coordinates. What about theta? Well, if we put theta equal to a constant, then I'm not allowed to rotate. So if I think about all the points that have theta equal to pi over 3, then I have to be along the angle that represents pi over 3. I could use negative radius, I could use positive z's, I could use negative z's, but I cannot rotate away from that theta angle. So this is actually going to generate a plane. And then we have one more, and that's z equals 3. Now z in cylindrical is just like z in rectangular, so this actually does generate a plane. So we have to be careful because some of the things that we have known for so long, they don't work the same in cylindrical coordinates. Like r equals 3, this is not a plane. It's a cylinder.